Vector operations. When you see a problem like this, I'm going to give you two vectors, maybe three, maybe four, five vectors. And I'm going to use the just combinations of what you see up here, where you have, u plus v, 3u, 2u minus v. You have all these different ways of writing out combinations of vectors and scalar products. What do I mean by scalars? What up here is a scalar? 3 is a scalar, and 2 is a scalar. I'm scaling it larger or smaller, like 1/2. So basically, like numbers that you multiply by, coefficients, what normally you think of, those are scalars. I'm just doubling its size. Like when you draw 2 of them last night. This is the same idea. So when you do this kind of stuff, I'm literally going to do what it says to do to my two vectors. Best thing about this is it's just like it sounds. You have two components. So look up here. What you see up here is called component form. It has two parts, a horizontal part and a vertical part. So when you add vectors together, you're going to add like components. So if you kind of write the first one out, it looks like this. Vector 1, 3, negative 3, plus 4, 7. That's literally adding u plus v. So you get this situation right there. So if I add that together, what do you think it is? 5, 4. Done. I want you to take 30 seconds and do the other two. If we continue in this, here's the answers. What you see on the screen is literally just order of operations. Okay, look over here at this one. The more important part is when I look at like part C, you see 2u minus v. Order of operations is going to make the difference between getting these very easily right or what you think is right. Okay, so if you're over here, I'm going to have to multiply by 2 first. That's what I multiplied by 2 to get that. And then I just took this vector and combined it with the one up top. And I got negative 2, negative 13. Any questions about... And this would be... the instructions here probably would say something to the lines of... perform the operation indicated. Maybe that's addition, maybe that's subtraction, or maybe it's just multiplying the scalars. You won't see division here. Okay? Dividing vectors is not really something that you do. Division would come in the form of 1/2 u. So really you're dividing it by 2, something to that nature. But it'll be represented usually by multiplication. All right, let's go on to the next example. Unit vectors. So, first part I want to introduce what a unit vector is. A unit vector has a length of 1 only. So, by length I'm referring to what name? Magnitude. Good.
With unit?
Okay. Now, when I say the word unit, I'm not... Your units could be feet or inches or mile. It doesn't matter. But when you were to find its magnitude... in whatever quantity you're working with, it would be 1. And, I mean, take for a second. What's the magnitude of the vector you see on the screen right now? Try again. Try again.
0.
I am appalled. Shh. Listen, I'm embarrassed. The fact that most of you right now were just simply yelling out a random number. Okay? No education behind that guess. You know that's not what you do in my classroom. Look. Yesterday I taught you 2 things. I taught you direction and magnitude. What is the formula for magnitude? Perfect. It's the Pythagorean theorem. So, a squared plus b squared. 13. Square root that number. That's my magnitude. I know the square root of 13 is not 1. So it's a lot more. So this is not a unit vector. Okay? Now with that thought, let me show you something else. What you see on the right side of the screen are, in quotations, the unit vectors. We can have vectors of any direction become a unit vector. But we have some very, very specific unit vectors. The vector that goes along the horizontal, we call I. It has a coordinate vector of 1, 0. This is for future reference. We'll get to it later. The vector that goes along the y-axis is called J. It has the components of 0 and 1, meaning it goes up 1, but it doesn't go left to right at all. I goes right 1 and doesn't go anywhere horizontal or vertically. Okay. A minute ago you said this was true. And so what we see here is that we can find out the magnitude of A and B. And A and B turns out to be just -3 and 2. And so when you look at that, you've got this component, or this calculation. In order, the instructions for this problem, listen, the instructions for this problem are going to sound like this. Find a unit vector in the same direction as the given vector. If you were to find the direction, right? Yesterday we said direction was theta equals tan inverse of b over a, of x over of y over x. And I could give you that angle measurement right now, and that vector is going to be headed in that same direction. I want to keep that direction, but I need to change this magnitude so that it's 1. Real simple way of doing that. This is what happens. If I can find its magnitude, I'm just going to divide both components by that magnitude and leave it. You could give me decimals, but I don't even need that. It's actually easier for me to grade if you don't.
Where'd you get 9 and 4?
Don't answer. You look. You tell me. Think. Shh. What is A and what is B? Okay?
There would be a time where you would find the magnitude of that.
Oh, yeah. In fact, shh. We'll do that in just a second. Shh. Next. This is really important. This concept right here, where it says find the components. Shh. Listen. Look at this. With our word problems, we typically have given information that's in context. Something is occurring at a certain angle measurement. It has this amount of force behind it. It's going to be terms of things that you talk about, forces and angles. If you're talking about a plane flying, we're going to do an example in a minute. It talks about a plane is flying due east. Okay? We know that the plane itself, in terms of in the cockpit, it's traveling 450 miles per hour in terms of its measurements. We know that it's actually flying due east, but in the plane, it's not registering due east. At least not their angle measurements, because there's a wind affecting that. That wind is blowing at an angle of bearing 60 degrees, and it's 65 miles an hour, which is affecting my trajectory. And we have to be able to calculate how all that's affecting the plane. So the plane pilot has to decide on how is he going to change according to the wind to keep his plane on the path. And this is part of the process you're going to work with. Here you have a vector that has a magnitude of 6 and a direction of 115 degrees. In order for us to make the word problems easy to comprehend and easy to process, I need to be able to go from this vector information with 6 and 115 into something like x and y. Because you have a bunch of vectors all acting on some object. If I can just find all the vectors, find all the components. Huh? Slightly. Did you forget something?
Are you still recording?
Yeah. Okay. Anyway. All right. You're going to type in, so that's the magnitude, or the magnitude goes here, and it goes here. I'm going to put in my sign of 115 here and here. Tell me what the components are for this vector.
Is it supposed to come out negative 5.4?
Good. So we plug it all in. It looks like this. Okay. For this part, that's it. Okay. Now, the word problems are going to put it in context, and so you're going to have to decipher that, but we'll get there in a minute. Questions here said, find the components of the vector if the magnitude was 6 and the direction was 115 degrees. No big deal. The question said, find the vector components for a vector that has a magnitude of 6 and a direction of 115 degrees. I mean, if you think about it, that's not a word problem either. If you think about what we're doing, you're looking here at, like the first part, this part right there, V, magnitude of V cosine theta, and magnitude of V sine theta, they're equal to X, and they're equal to Y. So you really could say that this part is X, and this part is Y. Mm-hmm. Well, that would just show the vector visibly, but you don't have to do that quite so much. Let's move on to the next question. Any question? Well, anything before we move? Okay. Find the magnitude and direction for the following vector. Or vectors. Do this, and I want to see what you come up with, and we'll talk about it. When you find magnitude and direction, first of all, why did it go back there? Who knows? All right. First of all, listen. First of all, we have the formulas here. Not going to give you those. Not going to give you those. Memorize them. Meaning, do enough work in class or homework to memorize it, because it's the Pythagorean theorem. You don't need to have it memorized. Okay? Tan inverse. Maybe you don't know that one, but we've been using that for a little while. Learn it.
What do we use it for?
We've done it in the past to find angles of sides of a triangle. But look at this. It's this part right here. If you're going to add 180, if x is negative when you do this piece right there. If the denominator for a is, if that number is negative, i.e. right there, if that number is negative, you need to add 180 degrees to your angle measure. Okay, here's why. If I graph that vector, it's right here, right? Well, you got 68.2 degrees. Does that look like 68.2 degrees to you?
Looks like the opposite.
It's 180 degrees opposite 168, right? Whenever you do tan inverse and your x is negative, the answer that you get is 180 degrees off. Shh. So whenever you get x is negative, you must add 180. Okay, get in the habit. So here we have u is square root of 13. Theta is the 33.7 degrees. Tangent of inverse of all that gives you 68.2. We've got to add 180 to get 248.2. Which makes sense, right? You're way down here in the third quadrant, so it better be between 180 and 270. So there it is. Magnitude here is 29, square root of 29. Questions? Mm-hmm. Yep. So we did tan inverse of negative 5 over negative 2, which gives you 68.2. But x is negative, so I had to add the 180. And this one was okay because it was positive. Yep. Okay. The next example looks like this. Shh, listen carefully. Shh. I'm not laughing. This is not a joke. You won't be laughing either when you see this on a test. This takes a little bit of thought, so listen. Alright, so with the understanding of bearings, you can kind of look at the picture here, and you can see I have a vector right here that's bearing 65 miles per hour. Shh. So the plane's starting off at that point right here. It's headed at this vector. That's the wind. The plane ends up traveling this direction. In order to compensate for the wind blowing it one way, it's got to turn into the wind. So it's actually going like this. Right? It's headed in a diagonal fashion, but because the wind's pushing it back, it makes it go east. Okay? If I headed due east and the wind's blowing against my left side, I'm not really going to be going due. If I'm headed that way, the wind is going to blow me over a little bit. So we end up hitting southeast, which is not what the plane needs to do. So the plane is going to have to turn into the wind a little bit. The question is, what bearing does the plane need to head? And how fast is the plane actually flying after it factors in the wind velocity? Okay?
Is that actually a real thing?
Oh, yeah. So, what we're going to do, and this is the concept that we want to learn. When I have to combine vectors, I want to put my vectors in a process, listen, so that I can add their components. Right now, I have no components of either vector. There's two vectors that I'm worried about. The wind vector and the plane vector. The resultant vector is the vector that you see right there. Okay, now my picture's not drawn to scale, but the plane does something, changes its angle so that its final trajectory actually is due east. And we have to figure out what did they do to get there. Okay, so the first part is, let's talk about, the easier piece is the wind. And so I'm going to talk about the vector, the components of, we'll call it vector W for wind. Okay, so if we have W, so vector W has a magnitude of 65 and a direction of what? Because it's not 60. What do we know about this angle? Really what I'd love to know is this angle right here.
Oh, well, it's 90.
Shh. Okay, that's equal to 30 degrees, right? So if that's 30 degrees, then that's the actual direction of my vector. And so that's what I'm going to use when I write this out. And so we're going to have, it's equal to the magnitude, because that was 65, times the cosine of 30, and then 65 times the sine of 30. W for wind. This is the wind vector up top, and this will be, we'll call this the bottom one P for plane. Okay? That's totally doable. That's done. I just need to put it together, put it in my calculator. I've got an actual result. But hold on a minute. In order for me to find the resultant vector, I'm going to be doing basically, we want to do, we'll call it, since that's vector V is equal to vector W plus vector P. Okay? These are just vector symbols. If I want to get that final vector, I have to add those other two vectors together. Do you remember how we added the vectors together when I gave it to you in the component form on the very first example? Added x's, added y's, and I got the x and I got the y.
Where's P?
P is the vector of the plane. It's at the bottom. I haven't done P. I haven't done anything with P yet. Okay? So P would be this vector down there. Shh, listen. And so, here we go. I'm going to leave vector W just kind of right here for now. Let's write out what vector P would end up being. Now we have a problem with vector P because we don't know everything about it. So let's just write it out symbolically. Vector P would be what? 450. P's right there. It's the trajectory of the plane. So it's 450 cosine. What's the angle that it goes at? It's just theta. We don't know. That's my problem. I don't know what theta is. Comma, 450 sine of theta. Shh, listen. Listen. Now, I can do this, but what's our biggest issue? I can add the x's together because they're right over each other. Right? Look here. There's an x, there's an x. There's a y, there's a y. I can just add those together and be done with it, except for the fact that I don't know theta. That's a problem. So I can't complete this until I know theta. But let's go back a minute and let's look at what do I know about the final vector. Shh. I know part of its components. Okay? I know that V is going to have which component which component is known? I know the angle, but that means I can know the y component. 0. How do you know that that's 0? Because it is horizontal. Remember, the x component tells you how far left and right to go. The y component tells you how far up and down to go. Well, if you're headed due east, you're not going up or down at all. So this is the one element that you had to just recognize. This is part of the step of faith you had to take. Just listen. So now, if I know this, then what I can do is I can set up a little equation. Remember earlier I told you that you can take your y components and your x components and add them together and set them equal to your x and y components here. But I don't know the x component. In fact, I can't know it. But I do know the y component. So let's set up our y equation and see what we can come up with. And so for the y component, we're going to have this 65 sine of 30. Alright, so to finish up this problem, we started here. We've written out the y components, okay, the two y components here and here. We knew from the direction, this is the plane is actually going to be moving east. So the vector for v is something we don't know for x. We don't know how long it is, but we know that it doesn't have any y component. It's 0. So we can set the two y components here, since we're adding the w and p together to get this y component. We're adding the two y parts together and setting it equal to 0. And we can go ahead and work that out, and you get this kind of data. So we figure out that the actual angle we're looking at is negative 4.1 degrees. If you do inverse sine of that fraction, negative 32.5 divided by 450, then that should be a 50 right there. You're going to get that value of negative 4.1. If we go ahead and think about the vector, if you look up here, this is a 90-degree angle, but it's a little further down past 90. That distance theta is our negative 4.1. So if we take that and think about how far that is, that tells us that 90 plus the 4.1, if we're talking about bearings, remember bearings goes from the top all the way down to here. So that's more than 90 degrees. In fact, it's 94.1 degrees. So that's going to be my bearing. The next part we had to figure out was what's the actual magnitude. So in order to do that, I have to figure out what this x component is. Well, I'm going to go back over here. Now that I know what theta is, I'm going to plug, so it's going to be this x plus this x, and I'm going to plug in negative 4.1 there for theta, and then I'll work that out, and it'll look more like this. So it turns out that you're going to get 505.1 as the x component, and because I only have one component for x, it's just 505.1 comma 0. If you use Pythagorean theorem on this, you're going to find out that the magnitude is equal to just that component, because if I square it, then I square root it, nothing's going to happen. And so then you have 94.1, which is my theta. That was my bearing down here, and that's the solution to the problem. Kind of tricky problem to work through. Pay attention. This is actually worked out in your book if you want to see it a little bit more organized. But you feel free to go back and watch that, or watch this video, or go back over the problems at hand. Otherwise, the homework assignment that you're going to need to do is here. It's a couple of problems on pages 464 and 465. You will be turning in some of these problems tomorrow for an assignment. So if you get a head start on it, great. If not, you'll be able to work on it tomorrow in class.